I hope I usually
Okay, today we're having Daniel Brennan from UC San Diego who's going to tell us about the Callan Rubakov effect.
great. Thank you very much, and thank you very much for the invitation to talk. It's always fun to talk to UC Davis people. Yeah, so today I'm going to tell you about some work I did on the Callan Rubakov effect. And this is a phenomenon that happens when you have massless fermions scattering off of a monopole. And so the picture we have in mind is we have some sort of singular monopole in a four-dimensional U1 gauge theory. And we can think about this as just a Dirac monopole for the moment. And what we want to think about is just some ball, a very small ball that's sort of cut out of space-time, and we have magnetic flux coming out of it. And so the Callan Rubakov effect happens when you have massless fermions that are charged that scatter off of the monopole. And in particular, we're going to be focused on spherically symmetric monopoles, and we're going to look at only the S-wave scattering. But what happens is that because of the spin-orbit interaction, or the interaction between the magnetic field and the spin of the fermion, there's actually no angular momentum barrier, and these fermions can tunnel into the actual core of the monopole and sense the UV physics that's inside of the core there. And so this is very cool because you can actually study this semi-classically. So you can do this in a very weak coupling expansion. And it's nice because there's actually some UV complete theories where we can study this. And it's also very important for gut theories because it can catalyze proton decay. This is sort of the original setting where the Callan Rubakov effect was studied, where you imagine a proton scattering off of a monopole, and it turns into a positron plus a neutral pion. And this is very cool because Callan studied this sort of directly, but you could also infer that this sort of process, as Rubakov did, by studying the axial anomaly. And yeah, so it's very cool. But in recent years, we've been revisiting this. And the reason is because of some confusion that sort of goes back to the original papers. This is sometimes called the semitone problem. And the idea is that if you have, for example, an electron, a single fermion that scatters off the monopole, it will turn into some conjugate particle, say like a down quark. And then you get a bunch of other stuff out here, which I'm not going to write down for the moment because it's confusing. But this is sort of constrained by symmetries. And what it looks like is a bunch of fractional fermions. And I'll explain exactly what I mean by that in a moment. But the point is that it's something that doesn't necessarily make sense in a weakly coupled perturbative gauge theory. And so in a sense, it's outside of this perturbative regime where we have total perturbative control. And so there have been sort of a few different approaches to explaining or trying to explain this phenomenon. And they fall into sort of three general categories. So the first is that we can interpret this as some sort of density matrix or some sort of mixed state. And this idea originally goes back to Callan. But this is sort of not really a good explanation because the result is that you're only conserving gauge invariance up to statistical probability. So that's bad. Another sort of class of yes, please.
Question about that. I mean, if you literally mean a mixed state, then isn't it just isn't there just a problem that the initial state is pure and so the final state needs to be pure? Is there?
That is also true. Yeah, that is also another problem with basically unitarity.
Okay. Yeah, it just seems like it's not unitary.
Yeah, it's very bad. It's sort of, I'm almost
Okay.
listening it for historical reasons.
Okay.
Good. And right. So another sort of class of solutions is that people have conjectured that there exist sort of extra non-perturbative sectors to the Hilbert space that sort of only exist in the presence of this monopole. And this has a bunch of confusing features. And essentially the problem is that it's unclear how you would see these in a UV complete, weakly coupled gauge theory. And there's been a lot of confusion about this even lately, and I'll touch on some of these solutions during the talk.
So maybe you'll answer that, but you're going to say what that means. In other words, what does that predict for the ...
Yeah, I can tell you briefly what it means. What they're saying essentially is that it's fine that they're fractional fermion states. They only exist in this part of the Hilbert space, and so you shouldn't be. And the Hilbert, and so the monopole itself is a non-perturbative element, and so the idea that we should be using perturbative expectations is bad. I don't agree with this sentiment, but I think that is some of the things that have been said.
So they would have to tell you how detectors respond to these things.
Exactly. And to my understanding, they do have not.
Okay.
That's my understanding. Good. And then, so the third sort of class of solutions is that there are just some additional interactions that have been missed in the sort of analysis, in the traditional analysis. And so this is where we're going to be living today. We're going to propose a new type of mechanism that could potentially explain both the Callan Rubakov effect and also would resolve this issue of fractional fermion states not making any sense. And but to be fair, I have a few caveats to this. So as I said up here, the in these fractional fermions are sort of constrained by symmetries. If you are working with massless fermions, you have a certain set of symmetries, and they tell you in order to preserve these symmetries, you have to have something here that doesn't really make sense. I'm actually going to be working in the case where there are massive fermions. And there's a couple good reasons to do this. The first is that, well, that's what we sort of have in the real universe. So maybe you want to talk about massive fermions anyways. So for phenomenology, they're important. But then also they serve as a nice IR regulator. And that's sort of, IR issues are sort of a big problem in QED, but also, as you'll see, those sort of things will be confusing in this massless limit based on the analysis I'm going to show you. But the problem with massive fermions is that it actually breaks a large number of symmetries. Breaks, for example, a lot of the chiral symmetries, and these are the symmetries that tell you there has to be this problem. So technically, when you are adding a mass, you are not technically required by the symmetries to have this issue. However, you would expect that if you're scattering at energies that are sufficiently high relative to the fermion masses, that you get this approximate symmetry back, and you should still have a similar behavior. So yes, so this is going to be sort of the setting of our talk today.
So is in some way your picture is that in the massless limit, you would normally say, well, chirality flips go to 0 because that's it. But could I interpret maybe what you're about to say is that somehow the chirality flips are not suppressed in the chiral limit because of some interactions with the monopole. Is that too simplistic or?
I think that's about correct. Yeah, I think that's a good intuition.
Okay.
Yeah. Okay. So right. So I wanted to sort of start by reviewing the sort of original analysis, or I guess which now the standard analysis of the Callan Rubakov effect. Okay. So the setting we're going to take is some 4D SU2 gauge theory. I'm going to take 2 times NF file fermions in the fundamental representation. And I'm also going to add 1 scalar field in the adjoint. And in this theory, I'm only going to allow gauge interactions and plus a potential for the scalar field. So if I take a potential, let's see, which is our standard Mexican potential, then our UV SU2 gauge theory will flow in the IR to just a U1 gauge theory. And when these fermions will directly become Dirac fermions of the infrared. And I'm going to set the Higgs Vev to this parameter V, and the UV cutoff scale for this infrared theory is going to be set by the mass of the W boson, which is the gauge coupling times V. So in this RG flow, there are going to be smooth monopoles of the SU2 theory, which flow to Dirac monopoles of the U1 gauge theory. And as I mentioned earlier, we want to take a nice simplification, and we're only going to work with spherically symmetric monopoles. And for SU2, that turns out to only be a minimal monopole. And that has to do with the fact that the gauge connections themselves are not rotationally invariant, but they're rotationally invariant up to a gauge transformation. So I'm taking here T to be the generators of my SU2 gauge Lie algebra. Okay. So we're also going to work with BPS monopoles just because we have those solutions. Essentially the idea of the BPS monopole is that after we write down the solution, we essentially take the limit where the potential goes to 0. So we're really just fixing the Higgs Vev at this parameter V, and then we're sort of forgetting about it. And the reason why this should be fine is that really turning on this Higgs potential really just sort of acts to squeeze the core of the monopole. And so you sort of expect all of the sort of long range IR features to sort of be the same. Okay, so the connection for BPS monopole, you can embed along the diagonal of the SU2 gauge field with this Dirac monopole. So this is in the singular gauge. And then you have this sort of off-diagonal component. This, where the signs are all correlated. And you have a Higgs Vev, which is also diagonal. And here there are these functions M of R and H of R. So the idea, for example, for H of R is that the Higgs Vev is approximately V at infinity, but then near the core, it goes to 0. This is like 1 over R, which goes like the mass of the W boson. And this M part, this M function here, which is like the profile of a W boson, falls off exponentially fast. This goes like e to the minus mw times r as a function of r. So what that means is that in the infrared, so in the IR, the gauge field solution just approaches T3 times A Dirac, and the Higgs valve approaches B times embedded diagonally. Okay. So to talk about the scattering off this background, what we want to do is we want to look at the bosonic perturbations in this background. So it turns out there's only really two. So the bosonic IR degrees of freedom. So the first is that there's clearly going to be the IR photon. And that's just because that's all of the gauge transformations essentially can commute with the UN gauge transformations commute with this solution. So we have this IR photon in the infrared, but there's also actually a charged scalar field in the core at R goes to 0. And the way to see that is now it's like look at the full BPS solution here, and you can look at how it transforms under the IR gauge field. Essentially, since T plus and minus does not commute with T3, the gauge transformations will act like e to the I phi. And if I want to work a notation where this is, they have charge 2, where the fundamental representation has charge 1, or plus and minus 1. So what we have here is that there's actually some sort of Goldstone mode, if you'd like, that would make this solution actually gauge invariant. And we want to treat this Goldstone mode phi as a physical degree of freedom that's totally localized at the core and sort of has a profile that falls off exponentially fast.
So this is a normalizable mode, right? This is
Completely, that's correct. So what you can do is you can actually take the solution now that we have up here, and you can actually just plug it back into the UV Lagrangian. And if you plug it back into the UV Lagrangian, what you'll find is that there's an effective quantum mechanics for this phi degree of freedom, which is just given by a particle on a string, or on a ring, sorry. That'll be phi dot minus 2.
sorry, is this phi, did you say that this phi shifts under gauge transformations or,
That's correct.
but phi is only a function of t, so how does it transform? Can you say more about that, or is this gonna take you way off your, am I blowing you off?
No, that's not at all, Marcus. So phi transforms like the gauge transformation at R equals 0.
Ah, okay. So it shifts by just the gauge transformation at x equals 0.
That's
not
correct.
the derivative of it, or does it? Is it like a Goldstone? Like it shifts just?
Yes, it's a Goldstone.
Yeah, so it just shifts by omega at x equals 0, or whatever you call that phase.
Yes, exactly.
Okay, I got it.
Yeah.
Thanks.
Yeah, no problem. And right, and so since this is a U1 Goldstone, it's also a periodic scalar. And in this convention, it's 2 pi periodic. So I haven't given it any sort of physical length. Okay. So sorry, I'm going to rewrite that. Okay, so this is something we've all quantized at one point or another in our careers, mostly in school. And so we know that it has a Hamiltonian, which is given by essentially the free particle in a ring, which is just p squared. And then it also couples to this gauge field. So as I said, A0 is the time component of the gauge field at R equals 0. And so if we just quantize this, what you find is that the Hilbert space is given by a set of integer states, which are diagonalizing this, the momentum operator. And then this extra term has the effect of saying that the charge n state sources a bulk electric charge 2 times n. And so the idea is that this dionic degree of freedom at the core of the monopole, if you kick it so that it's a winding mode 1, then what you're effectively doing is you're kicking the W boson and you're exciting it into its first excited state. And what that does is it turns the monopole into a dion. And because of the charge quantization conventions I picked, it's going to be charge 2. And so this is important because Callan Rubakov effect is essentially the interaction of the dynamical fermions with this dionic degree of freedom. Okay, cool. So now we can couple the theory to the fermions. And so since we're in the sort of semi-classical limit, what we can do is we can just perform we're looking at IR scattering. So what we can do is we can look at the mode expansion of the fermion fields in this monopole background. And so since everything we're working with is a spherically symmetric background, we can also expand in angular momentum representations. And we'd like to just restrict to the j equals 0 sector, which traditionally is what people do when they study the Callan Rubakov effect. And the heuristic reason is that the j equals 0 mode has no angular momentum barrier. So it's what can really tunnel in and see the UV degrees of freedom, whereas all the higher angular momentum modes have some angular momentum barrier that sort of repels them away from this UV interaction. And yeah, so this is a consistent thing to do to leading order. Essentially because this phi degree of freedom is also spherically symmetric. It couples to the system in a spherically symmetric way, so everything is fine, at least to tree level. Okay. So the IR mode expansion happens to be very simple. So if we'll give the fermions some index A, where A is sort of like a flavor index, and we can decompose it into, so this is the SU2 fermion, which is in the fundamental representation. And we're going to decompose it into the U1 gauge field components with psi plus and minus. Okay, put that down. And it turns out that these psi plus and psi minus are polarized, and have solutions that go like this. So they have the positively charged fermions are ingoing solutions times some constant spinner, and the negatively charged fermions are only outgoing solutions that also times also a covariantly constant spinner, and these spinners are polarized with respect to the radial direction.
Sorry, can I ask, I thought you were you were talking about massive fermions. So these guys are paired up. And so
that's right.
So I'm a little confused because I mean, if they were massless, then the plus and the minus would just be independent massless modes, right? But now
that's correct.
And so where's that putting
good
in here?
Good. So right. that's my, I'm sorry. So the idea, sorry, here I want to just review the old story. So I'm
Okay,
just stick to massless.
Yeah, because these things are on in the light column, yeah. Okay,
Yeah, that's
cool.
right. So in a bit, we'll reintroduce them and pair them, and it'll hopefully make more sense. Good. So with this decomposition, you can see that sort of the effective, all of the dynamics are put into this Grossman valued, essentially it's a 2D fermion. These chi A's are left moving 1+1 dimensional fermions. These chi tilde A's are right moving 1+1 dimensional fermions. So the sort of scattering problem is effectively a two-dimensional problem. So what we have, I'm going to draw our two-dimensional space. So this is the time direction. This is the radial direction. And what we have is we have chi fermions that are left moving, and they have electric charge 1. And we have a bunch of chi tildes, which are right moving, and they have electric charge -1. And so this is clearly a non-unitary problem, unless you have a boundary condition. At r equals to 0. And so there's essentially only two sets of boundary conditions you could write down, or two classes of boundary conditions. But the one that's literally handed to you by this UV model is that chi A is equal to e to the I phi chi tilde A. So this preserves the SU2 and F global symmetry of the UV model, and it preserves gauge invariance. And that actually fixes this interaction, the boundary interaction, to be this way. And so now what we want to do is we want to sort of understand the IR scattering by matching these IR, essentially matching this IR mode onto the UV degrees of freedom. And indeed, if you actually solve, or sorry, a nice consistency check rather, is to match this boundary condition onto the UV zero energy solutions. And what you find is that exactly this is reproduced by the exact solutions to the Dirac equation in the full SU2 monopole solution. Cool. So, so maybe we should talk about a little bit about the physics of what this means. So what this is saying is that in terms of gauge charge, we said that the chi's have gauge charge +1, e to the I phi has charge +2, and the chi tildes have charge -1. So what this means is that as you scatter in a chi field, it'll bounce off the boundary as a chi tilde field, and it will deposit electric charge into this phi mode. However, that's actually a problem. So the problem, which is essentially the source of the sematon problem, is that this phi degree of freedom is very heavy. The Hamiltonian that I wrote down earlier was essentially mw/2 times the momentum squared plus source term. And you can see that any excitation of this phi degree of freedom will require energy of the order of mw, which is the UV cutoff. So you need energy that's so parametrically large in order for this process to actually deposit energy into the dionic degree of freedom. Essentially you need enough energy to kick the W boson so much that you excite it inside the monopole core and you transform it into a dion. So essentially the phi cannot conserve gauge charge in this way. So the way that this was originally approached, this problem was originally approached, rather, was to work with a bosonic dual. So essentially what we're doing is we take, for example, the chi fields, and we can introduce a conjugate scalar field, which I'm going to call HA. And essentially what we're doing is we're taking the current for one of these fermions and just saying that the current is the derivative of some bosonic field. And we're going to do similarly, we're going to do the same thing for the chi tildes. And then what you can try to do is to construct boundary conditions that preserve all of the symmetries that we want in terms of these J's, or what we're really going to do is write it in terms of these H fields. And so the way you can do it is you can just try to construct some matrix, which I'm going to call R here, which relates the ingoing to outgoing currents at the boundary at R equals 0. And as it turns out, the symmetries of this problem actually uniquely fix this matrix R. And it takes this kind of funky form. So it has this diagonal term, which is just this tree level scattering that I was talking about, where chi transforms into chi tilde. But then there's this term which is fully populated. So what I mean, for example, for nf is equal to 4, is that R is the matrix with, sorry, I'm writing this in the quick way. So it's totally populated matrix with plus or minus a half in all of its different entries. And so there have been many different ways to sort of think about this. Oh, well, okay, so first of all, this matrix.
2, right?
Sorry, say it again.
I mean, NF equals 2. You have 2 NF fermions.
Yeah. Yes, thank you. I think I actually, this should be a 2. Yeah, I think this is the correct answer. Right. So essentially this matrix has all of the physics of the Callan Rubakov effect. And essentially what you can see that by well, okay, maybe it's not the smartest way to do this, but so if you imagine you send in some psi1 and some psi2, so what you can do is you can transform that into saying I have some incoming current, which is J1 plus J2. Sorry, I think I should use upper. Say these are positively charged. And what you're going to find is that J out is J3 tilde plus J4 tilde, which is psi minus 3 plus psi minus 4. And so this, if you essentially embed this inside of the standard model, what you'll find is that this can describe, for example, proton decay. If this is like the two up quarks, this will be a positron and a down quark. But what happens is that if you look at just, for example, scattering a single fermion, say we'll take psi1, this is the same thing as scattering pi1 coming in, so +1. And in terms of the bosonic fields, each one, this will actually look like a kink solution. So this will be some sort of incoming soliton where this jumps by 2 pi. And so if you just follow the mathematics that we've set up in this problem, what you'll find is that H1, for example, transforms into H tilde 1 minus 2 over NF, and then the sum of all of the other outgoing HAs, H tilde A's. And if you transform this back into fermionic language, sorry, I should actually tell you. So when we introduced these bosonic degrees of freedom, the way to transform back is that the HAs are actually like a phase degree of freedom for the chi's, and similarly for the chi tildes. And so if you just literally exponentiate this formula for the incoming h's going into outgoing h's, you'll find that psi goes to psi tilde. And then you also have this outgoing mode, which is created by this operator, phi tilde bar, for the 1 over 2 over n. So you're introducing the state, which is like the nth root of some good operator. And this is sort of the fundamental problem of the Callan Rubakov, or understanding the Callan Rubakov effect. And in recent, there have been many ways people have tried to say this. Some have said that you can think of this as some sort of like soft radiation, which is sort of goes back to the idea of Polchinski. And more recently, people have said that, well, this doesn't actually make sense. It only makes sense to take the nth root of an operator if you actually also introduce some ZN gauge theory. And so the idea is that this is why you are attaching some sort of topological verb. So in this ZN gauge theory, you are assigning this nth charge operator the charge 2, because it has this 2 up here in the numerator. And so you're attaching, you can try to make sense of this if you attach a topological Zn Wilson line to the outgoing state. And this is what people have been saying as some sort of non-perturbative sector of the Hilbert space. So this is the idea that's recently been put forth about why you would need some topological line to describe the Callan Rubakov effect. What's up, Marcus?
So I know this is not what you're talking about, but you're giving a very clear introduction, so I'm going to keep bugging you. For the
Sure, no problem.
gauge theory thing, this ZN gauge theory is not it's not part of the UV theory. It's somehow emergent or something like that. That's the story. Yes.
That's correct.
Okay. Thanks.
Yep, no problem. And I'd also like to say that it's unclear how it would be emergent.
Are you willing to say anything more about the Polchinski thing? I mean, is that sort of your point of view in some way, or is that, can you say a little more besides those words, or?
How about at the end? I'll come back to it.
Okay, that's perfect.
Okay, so now I want to sort of lead you down some maybe digression. And it has to go back to this quantum mechanics for this ionic degree of freedom. So we had this Lagrangian, which described a charged particle on a circle, on a ring, charge 2. And so there's a topological interaction you can add to this Lagrangian, which is pretty well known. It's called the theta term. Well, it's essentially, it's equivalent to a 4-dimensional theta term. But physically, you can think of this as turning on some sort of magnetic flux that threads this imaginary ring. And so when you do this, the momentum operator shifts. By a constant. And consequently, you also find that the Hamiltonian takes a different form. And so what you find is that shifting theta by 2 pi, so say it goes from theta equals 0, and you're in some state n. And if you adiabatically change to theta plus 2 pi, the state will also shift adiabatically to the n plus 1 state. So in particular, the ground state will shift to the 1 state. And so this will say that the vacuum will now source a 4-dimensional electric charge. And indeed, I mentioned the theta term, and that's because actually in our model, this can be induced from a 4-dimensional theta term. So let's take theta term. I apologize that I really like using differential form notation. So I'm going to write it this way. And so if we decompose it in terms of electric and magnetic fields, so it's essentially this term is proportional to E dot B. And so if we integrate the magnetic field along a concentric 2-sphere, what you find is that this is theta over 2 pi times the TR component of the field tensor, which then you can integrate by parts to get theta over 4 pi dot minus 2a0 at r equals 0. And that's exactly this term that we wrote down up here, where theta 4d is equal to, I think it's 1/2 theta 2d. Oh, other way around. And that's essentially because the dionic degree of freedom is charged 2. So what's nice about these 4-dimensional theta terms is that they can be induced from integrating out massive fermions with a CP violating mass term. So if we had a fermion mass, which is given by some real positive part times e to the I alpha, then what you find is that the 4-dimensional theta term that it generates will be alpha. This is a single charge 1 fermion, direct fermion. And as we know, there is a Witten effect that is associated to this theta term. And what that is it says that the theta term induces an electric field, or electric charge rather, on monopoles. The magnetic charge is going to be theta over 2 pi times, the electric charge. It's going to be theta over 2 pi times the magnetic charge. And you can show is that there's actually a charge density that is induced in the fermion vacuum, which falls off exponentially with the fermion mass. So when you integrate out this fermion and you have a CP violating mass, what you find is that the fermions actually form a little charge cloud around the monopole, which has a radius set by the fermion mass itself. And so what I'm going to claim to you, and then next show, is that the Callan Rubakov effect as a dynamically induced theta term. And this is how gauge charge will be conserved. Okay. So now let's get, oh, yes, please.
Yeah, so I heard different talks about the same effect, and they say something about rotor. Is that rotor connected to this theta term?
Yeah, that's right. So the rotor is actually this phi degree of freedom. This is yeah.
So
The idea of the
Does this theta have to be like quantized value? You can only shift it by multiple pi, or it's like a continuous thing, or if it makes sense to discuss the continuation of it.
Right. So in general, theta can be any value between, well, could be any value. And but what I was going to show you next is that when you have fermion scattering, you only induce a shift in theta that comes in multiples of 2 pi. And that's how there's going to be conservation. But in general, you could have, for example, a Callan Rubakov effect with a non-trivial theta term. Or you could consider the scattering where you have some other massive fermion that induces a theta term. Okay.
Sorry, I'm a little confused about, so what am I supposed to think about CP invariance? You say you're reducing a theta term, but your original Lagrangian was CP invariant, the theta is CP odd.
That's right. So theta is CP odd, and except that you have CP invariance, that theta is equal to pi and 2 pi, although there's an anomaly at pi. Oh.
Yeah. So, but is it, okay, so you can't get any value except the CP conserving ones, or what are you saying?
That's correct. So you would have to introduce some additional CP violating term and some other UV completion in order to get CP violating terms. You're right.
Okay.
Yeah.
I guess
Here, let me show you.
I don't know what role this theta, I don't know what you mean by an induced theta and what it's doing. Maybe you're going to explain that.
Yes, that's what I would like to do now. So hopefully that'll clear things up. Okay. So now I want to go to this the case of massive fermions. And so in the UV, I want to consider adding some mass term, which is so there's really an SU. Sorry. Of the IR theory, there's an SU2NF times SU2NF global symmetry, which act on the chi's and the chi tildes respectively. I want to introduce a mass term that preserves an SU, I guess the diagonal SU2NF. So I'm going to have mass terms. Actually, sorry, I think it's SUNF. No, it's SU2NF in the IR. Sorry. So I'm going to have a mass term that looks like psi plus A, psi minus A, psi plus conjugate. And in the infrared, we can use the same mode expansion actually, and you get a mass term. For the fermions, it looks like chi A, chi tilde A times M plus complex conjugate. So this is how I'm going to introduce the mass term.
In the UV theory, the global symmetry was just SU and F. No.
That's right. Yeah. So that's actually why I was hesitating for a moment there. That's correct. Yeah. So, or sorry, yeah, that's right. That's right.
So how can the UV and IR have different global symmetries?
Okay, let's see. Do this. So this is down here in the IR. So truly in the UV, the largest thing you can get is breaking SU2NF to SO2NF because you have fermions that are in a symplectic representation. So what I wanted to take is a SU-NF subgroup of that. So you can just pick a mass that preserves that. And then it turns out when you sort of decouple the positive and negatively charged fermions that you get a symmetry enhancement. However, the boundary conditions will actually break this SU2NF to the true SU-NF. The masses and the boundary conditions won't be compatible. So good. So now, if we do our bosonization trick again, you get some action that looks like this. So, oh, sorry. So first I want to, since we have massive particles, I want to combine chi A and chi tilde A into a single Dirac fermion, which then I'll combine into a single scalar field, which is no longer chiral, but you can think of it as this HA plus H tilde A in terms of the left and right moving bosonic fields from earlier. So now you can write the Lagrangian, or the action, I guess, in terms of this uncharged scalar field. So good. So this is also a nice trick here. So since H is a scalar field of charge +1, and H tilde is a scalar charge of charge -1, this lowercase h is actually uncharged. However, it does still couple to the gauge field. It couples by, so it's like the gauge field wedge d of h. Oh, maybe I'll use the lowercase a. Oh. Shoot. Okay, I'll write it differently. If you integrate it by parts, which is what I was going to do anyways, you get the TR component of the field strength times this little h, where h is just the sum over all of these bosonic fields. In a sense, it's the total field, h. And oh, of course, you also have these mass terms, which comes in cosine. And then you have a kinetic term for this gauge field, which has this r squared here from spherically reducing the gauge field. Okay, so this also couples to the bosonic dion degree of freedom. And that's it like this. So we have our kinetic term. And then when we integrated this by parts to get this form, we actually get a coupling that looks exactly like a theta term. So here, for the theta term, is like a, well, essentially you can think of theta effective as this boundary value of this total field h over 2 at r equals 0. So now we can think about the scattering. So I want to send in an HA.
Okay,
Oh,
sorry,
sending.
can you scroll up a bit.
Yes, please.
Little h is the sum of a positively charged and a negatively charged field.
Yes.
So why did they both contribute the same electric field?
I think it might be, maybe the way to think about it is, since you have a positive component that's left moving, you have a negative component that's right moving, they sort of both contribute to a current that's going in the same direction. Or a net current in the same direction.
I mean, maybe another way, maybe this is a bit confusing to me too, because normally we label the states by charge, like we diagonalize the charge, right? But now
Mhm.
it seems like you're taking linear superpositions of different charge states. I don't know what I'm really asking. I'm just,
Yeah,
a little-
that's fair.
Seems weird.
It's This is a slightly unorthodox presentation of the Lagrangian. It's just the T-dual version where I've dedualized the I think it's the R coordinate, I guess. Or it's still an equivalent system, and I think the nicety is that you have this boundary interaction, and I can show you now what I mean by what I meant by there's an induced theta term. So if we're sending in a capital H particle, the idea is that oops, there's some kink that's incoming, and this shifts by 2 pi. And then it scatters into an outgoing H tilde kink, sorry. Which also is 2 pi. And what you see is that the boundary value of H plus H tilde at r equals 0 will eventually shift by 4 pi. And so this leads to a shift in this H at r equals 0, 4 pi, which essentially says that there's a shift of the effective theta angle by 2 pi. And so then the proposal is that this is a way that the fermion vacuum preserves the electric charge through the scattering process. And if you sort of follow this back through the back to the 4-dimensional field itself, what we see is that this H kink, so these psi's are like 1 over r times some set spinner plus times e to the I h. And so this H kink is really like the phase mode of this 4-dimensional fermion spinning around on some wavefront. So there's some sort of finite charge packet, and the phase rotates by 2 pi in that sort of wavefront. And what this is it's kind of like an axionic mode. And that's why they're. Go ahead. I was just going to say that this is essentially why there is like this shift of a theta term. It's not really a shift of a theta term, it's a shift of the fermion vacuum that's induced by this scattering process. And you can see it just by the fact that the phase mode of the psi plus and the psi minus transform in opposite ways so that there's a total net effect.
I mean, in the beginning, you argued that it's hard to see how this localized mode could matter because it requires an energy of order MW to excite. But
That's
so
correct.
here, you're somehow, aren't you saying that it is being excited? So what gives?
Yeah, it's more like yeah, so it's not really like it's being excited because there's sort of like the spectral flow of all of the states. That's the proposal.
But if it has an
essentially
electric charge, the dion has a larger mass than the monopole because it has electric charge.
that's correct.
So doesn't this final state, it's a dion, so it's much heavier than the monopole you started with?
So good. So that's a great question. So yes, it is a dion and it has an electric charge. However, the quantum mechanics, which is sort of like, essentially how much mass or how much energy is inside of the W boson itself, has 0 energy because we have this spectral flow. But essentially the point is that the amount of charge is not contained in the size of the W boson, which is why the W boson is so heavy. There's a charge cloud here whose radius is set by the fermion mass itself. So really you only need as much energy as it takes to send in the fermion to excite this itself, or to induce this shift.
I thought that, I mean, the picture of this flow, you can draw this picture, right? Where, so the energy eigenvalues go like n squared, right? And so at theta equals 0, you just have that spectrum. But then all the non-zero ends have two positive and negative guys. They split, one goes up, one goes down, and the spectrum goes back to the spectrum, right? So if you follow the lowest guy, it ends up at n equals 1, but there's a guy that crosses it and it goes back down. But
That's right.
I'm a little confused because the scale of those separations is set by MW, no?
Yeah.
And so,
yes.
so if you're not right at theta equals 0 or right at theta equals pi, it's costing you an energy of order MW. You can't. So
Yes.
I don't. So again, it's hard to see why would that. How can that happen? How can that be unsuppressed?
Yeah, indeed. So good. So if instead of treating theta like just some parameter here, where I just like look at a spectral flow, indeed, like for example, as you're saying, if you take theta equals pi, then all of the states have energy of order MW.
Right.
Which is the main problem. I had not gone through to look if there's level splitting. I mean, my pet theory is that maybe there is, but I don't know. But I know if you sort of treat everything, well, if you treat it this way, it is suggestive that this is an effect that could happen. Yeah, and the fact that this like shift of the theta angle sort of has a change of the vacuum state, or deposits electric charge in the vacuum, which has parametrically low energies, is at least a nice picture, and some way that it could potentially, well, I think it's a nice picture, physical picture, but it definitely requires more analysis to see if there's some tunneling, or if there's some level splitting, or if this just doesn't happen because of the effect you guys pointed out.
So does this help clear up if this happens? Does it clear up what this final state is in this weird semionic case?
Yes, it would. Yeah, so good. So the claim, or maybe proposal. So the proposed, essentially the proposal I have is that the physics of massive fermion scattering is if you send in some charged particle into a monopole, it scatters off as its UV conjugate. So you think of mole as being in some sort of doublet, and so it's the other component of the doublet. And then the monopole, you also have the monopole, but you sort of think of shifting the dion degree of freedom, quantum mechanics, by 2 pi. So this is, in some sense, it's a dion. But really, what it's the physical statement is that when you do the scattering, the fermion vacuum, the outgoing fermion vacuum is not the same as the ingoing fermion vacuum, and you sort of shifted the electric charge in the vacuum by exactly the amount that you would need to conserve the gauge charge.
And so compared to the standard story, you're somehow saying that even now if I start taking the massless limit, you're saying that this is a chirality flip. Yes, I'm understanding your notation. Yeah,
Yeah.
and this is somehow unsuppressed, even if you take the fermion mass to 0. That's the picture?
That's right. So, yeah, that's correct. So this is maybe one reason why there could be level splitting, or one way to maybe motivate that there could be level splitting is that if this is totally unsuppressed in the massless case, perhaps there's a level splitting that's set exactly by, well, I guess you would say that the energy barriers perhaps get set by the fermion mass itself. But I really have no idea, so I should stop speculating. Yeah, good. So also there's a few problems with taking the massless case.
Does this conserve energy? If I can
Uh,
take incoming energy arbitrarily small and the dion has some finite mass difference from the monopole that depends on the fermion mass. But the incoming energy can be arbitrarily small compared to that.
right. So good. So if you had some incoming energy, it would have to be of the order of the fermion mass, maybe say plus epsilon. And then you would say that the difference in the dion mass is, well, it goes like m psi. I haven't computed it exactly. But then, yeah, so good. So if psi, if epsilon, say, is much smaller than m psi, then you could say that probably what happens is there's a bound state that forms between the outgoing negatively charged fermion and the positively charged ion. That would be the way I would expect the energy is conserved.
But that binding energy is order charge squared. So
But it's also negative, right? Or so it's like a negative energy. It's a bound state.
parametrically small compared to the dion mass splitting.
It doesn't go like q squared times m psi or something like that.
So in the, are you saying that in the massless limit, there's a whole bunch of states that somehow are missed in the conventional treatment? Because it seems like you're saying that there in the, for m psi not equal to 0, there are these states whose splitting is set by m psi. So you're saying, are you saying that somehow in the massless limit, there's a huge number of states that are just missed in the standard analysis?
Yeah, so this actually also goes back to your earlier question about the soft radiation. So if you take my picture literally and you take the m psi goes to infinity limit, or to 0 limit, excuse me, the radius of this charge cloud goes to infinity, but stays sort of a constant electric charge. And so you essentially have 0 charge density, but with a total finite charge. And I believe essentially what's happening is that there's an electromagnetic memory effect. So there's something captured at Scry plus, where you would see that there's sort of a bump in sort of a DC offset electric charge as the fermion passes, the fermion wave front passes Scry plus. That is sort of what I think the interpretation would be. And I'm not sure if that should be thought of as in terms of there being like a whole set of new states that are arbitrarily low mass or not. But I think that's in the sense, it's kind of like saying there's some soft radiation, but it's not really quite the same. That's sort of what I expect the massless solution is based on this analysis.
So we're about 10 minutes over. Are you close to your conclusion or?
Yes, sorry, I am. I have said almost everything I wanted to say. Yeah, I guess the final comment I wanted to say is that essentially what happened, essentially since the fermion fields, or all the fields in the theory, transform under some SU2NF times U1 gauge. Since there's the ZN redundancy, I believe what that means is that essentially anything that any process that tries to take away gauge charge from the monopole that's not in units of n, sorry, I believe this is 2NF, not in units of 2NF, will violate the global symmetry, violate the global SU-NF global symmetry. And so essentially what that means is that I believe the dion of charge 2NF is unstable to decay. And what that really means is that there is this in the original analysis, there was this psi A goes to psi plus A goes to psi minus A plus this nth root, psi tilde bar, or psi minus bar to the 2 over n. F. Sorry. 1 over nf. Essentially, the point is that if you do this process nf times, you are taking this to the nf power, and you could decay through this operator, which is a good operator in your theory. And if you think about integrating out the ionic degree of freedom, this is what you would get as contribution to the instanton Atoth vertex. So, so I think the comment I really want to make is that this proposal matches the original Callan Rubakov analysis when there was no fractional instantons. Sorry, fractional fermion states. And that's, I think, all I have for you guys today. So I'll stop there.
Questions?
Your job. Want to ask the question? So we just recently, can I just ask Ben, we recently had, this sort of reminds me of, we just recently had, since John's in charge of seminars, it's all monopoles all the time. And we recently had Anson Hook, and so he sort of had this picture, and he was making this, sounded like a similar point. I just want you to comment. My understanding was that he was also saying that there are these, as you take the fermions, he's also starting with massive fermions, that there are these bound states of these massive fermions, and they're getting bigger and bigger. So now, if you want to talk about the massless limit, you've got to decide, are you at fixed radius and then taking the mass to infinity, or are you moving away, okay? But now I think if we're talking about the massless limit the way we normally do, we would take the massless limit first, and then take the experiment, as far away as possible. And so his picture seemed to be that somehow that means we're always inside the monopole, and that was supposed to make somehow more sense out of these semitons. I don't know if I got that right even, so I mean, but I'm just trying to get you to comment, is something like that your picture also? You're saying this thing gets huge, as in this cloud or whatever, this gets really big when m psi goes to 0. So that means your detector is living in it. No?
Yeah, I think that's probably a cartoon of what I'm proposing. I mean, I'm proposing that you have some wavefront that goes through. Don't send in a plane wave, send in some wave packet to scatter off of the fermion. And essentially, you won't know that the scattering is done until it comes back and passes through you. And so if the mass goes to 0, in a sense, it sort of never really stops, and your wave packet is sort of order 1 over mw, then it sort of never stops scattering in the m goes to 0 limit. And that's sort of one of the reasons why I think that to properly account for this, you have to look at this asymptotic symmetries or asymptotic states at scri plus and minus in order to really take this into account. Because as you said, we usually have to work with some sort of IR regulator, and then there's something that's maybe unclear, but there's this other formalism where you don't have to do that at all. You just say asymptotic infinity, and then everything seems to work well. I've read Anson's paper, but I haven't thought as deeply about it as I probably should. I saw that he found these bound states as well, which made me happy. But I think there's still much to do. So.
And did you read Okui's paper?
I don't think so. Which paper is this?
Okay, Okui.
OKUI, Okui. He just recently put a paper out on this.
He also starts with the rotor, but I think he gets a different conclusion. As far as I can tell.
Yeah, I think so.
Oh, there are some papers that I think got the rotor coupling wrong. Okay. Yeah, I've read this paper because it loaded it at the end of the paper. Yeah, so some of the people who are using this original Bolchinski model, essentially you have to be careful about where essentially they're off by a derivative. And so it's like, are you measuring the change in charge or the total charge, I think is a mistake I've seen. I'm not sure if this is one of those papers or not, though. So I unfortunately cannot comment on this particular one. I don't remember.
Yeah, let's thank Daniel again.
Thanks, Daniel.
Oh yeah, thank you again for having me. It's always great to talk to you guys.
Are you still